ReplaceMe, network simplification via depth pruning and transformer block linearization. Dimitri Shopkovestris, NWSAI, ITMO University, Amr Ali Asris, NWSAI, ITMO University, Mediages, NWSAI, Valentin Med, NWSAI, ITMO University, P2 University, Samatios Lefnadis, NWSAI, Nikos Komadatis, University of Crete, Adam Forth, Archimedes Athena RC, Sergi Zavoriko, Polynom. That's right, we introduce ReplaceMe, a generalized train-free depth pruning method that effectively replaces transformer blocks with a linear operation while maintaining high performance for low compression ratios. In contrast to conventional pruning approaches that require additional training or fine-tuning, our approach requires only a small calibration dataset that is used to estimate a linear transformation, which approximates the pruned blocks. The estimated linear metin can be seamlessly merged with the remaining transformer blocks, eliminating the need for any additional network parameters. Our experiments show that ReplaceMe consistently outperforms other training-free approaches and remains highly competitive with state-of-the-art pruning methods that involve extensive retraining/fine-tuning and architectural modifications. Applied to several large language models (LLMs), ReplaceMe achieves up to 25% pruning while retaining approximately 90% of the original model's performance on open benchmarks without any training or healing steps, resulting in minimal computational overhead. We provide an open source library implementing ReplaceMe alongside several state-of-the-art depth pruning techniques available at https://github.com/mpasi/replaceme. 1 introduction. In recent years, transformers have achieved unprecedented success across a wide range of tests on both computer vision and natural language processing. Modern large language models (LLMs) typically scale up to billions or even hundreds of billions of parameters, significantly increasing the computational and memory requirements for both training and inference stages. This substantial resource demand poses a critical challenge for their wider practical deployment and usability. Due to the excessive size of modern LLMs, there has been significant research effort to make such models accessible to users with limited hardware capabilities. These efforts primarily focus on 3 key strategies: quantization, distillation, and pruning. Pruning, which is the focus of the current work, involves identifying and removing less important parameters or entire structural components to streamline the model, thereby reducing computational overhead without significantly compromising the performance. Structured pruning is different from unstructured pruning in that it focuses on equal contribution. This work was accepted and presented at NER IPS 2025 conference of 2505.02819v4CUS.C on 19th of 2026. Entire groups of parameters or layers, allowing their complete removal. This approach not only enhances hardware utilization efficiency, but also potentially achieves greater reductions in resource consumption. Importantly, it operates independently of the hardware type used. In this work, we focus on structural depth pruning, operating under the hypothesis that a contiguous set of transformer blocks can be effectively approximated by a single linear transformation. To validate this idea, we propose ReplaceMe, a novel training-free pruning method that replaces selected blocks with a linear transformation estimated from a small calibration dataset. It should be noted that most existing pruning methods require a post-pruning retraining phase, often referred to as a healing process, to recover lost performance. This retraining stage can be time-consuming and computationally extensive. In contrast, ReplaceMe preserves the majority of the model performance without any retraining for reasonable compression ratio scenarios. ReplaceMe generalizes depth pruning methods by introducing a simple yet effective linear transformation that compensates for the error caused by block removal. This transformation is subsequently fused with one of the remaining model weights, enabling seamless integration without adding parameters. The contributions of this work can be summarized as follows. 1. We propose ReplaceMe, a generalized method for depth pruning that can maintain model performance without requiring any healing process for reasonable compression ratios. 2. We conduct a detailed study on the estimation of a linear transformation with both analytical and numerical methods and under different objectives. 3. We provide detailed ablation studies for different calibration data, solvers, and LLM archetype features. 4. We validate the effectiveness and generality of ReplaceMe across diverse model families, including LLMs and vision transformer architectures like VT7. This paper is organized as follows. Section 2 presents the core methodology behind our training-free depth pruning approach. It introduces the framework for identifying prunable layers in large language models (LLMs) and estimating the corresponding linear transformations that compensate for the removed components. This section also discusses the selection of appropriate loss functions, regularization strategies to ensure generalizability, and the potential extension to multiple linear transformations for more flexible pruning. Section 3 then provides comprehensive experimental results and ablation studies demonstrating the effectiveness and robustness of our method and analyzing the key factors that influence its performance. 2. Method. Next, we introduce ReplaceMe, a novel depthwise neural network pruning method that balances simplicity and effectiveness to optimize model performance. Our approach is based on the idea of pruning multiple layers in transformer models and replacing them with a single linear transformation. It consists of the following key steps. First, we identify layers suitable for pruning by targeting those with minimal impact on performance in line with prior research. Section 2.1. Next, we compute an optimal linear transformation LT to compensate for the contributions of the pruned layers. Notably, this transformation is seamlessly integrated into the preceding layer, preserving model performance without introducing additional parameters. Section 2.2. Furthermore, we study the effect of regularization methods on the estimation of the transformation and show that this can be a helpful strategy to maintain balance between model performance and complexity. Section 2.3. Finally, we outline how to extend our framework to support multiple linear transformations, enabling flexible and informed pruning decisions. Section 2.4. Together, these components establish ReplaceMe as a practical and robust advancement in training-free neural network pruning. 2.1. Layer selection. Let's say our n times TBE the input to the ITH transformer block, where n denotes the number of tokens and hidden dimension of the transformer model. Then, typically the conventional transformer. 2. Multi-head, attention, norm MLP, norm multi-head, attention, norm MLP, norm multi-head, attention, norm MLP, norm block, 6 transformer blocks, multi-head, attention, norm MLP, norm linear transform. Figure 1. ReplaceMe compresses and accelerates LLMs by bypassing a contiguous sequence of transformer blocks illustrated by the red line while preserving model performance. This is achieved by inserting an estimated linear transformation matrix that maps the MLP output of the I*TH block directly to the input space expected by the I*+ n+1 TH block, effectively replacing all m blocks in between. Block can be expressed in the following way. E equals SI plus MHAI ln1 I Z1 Y equals MLPI ln2 I 2 Y equals YI plus MI 3, where MHA and MLP denote the multi-head attention MHA and MLP layers respectively, while ln1 I ln2 correspond to the layer normalization operators for the MHA layer and after the MLP respectively. The output of the attention subblock is denoted as Z, while my and lie present the output of the NLP layer and the transformer block respectively. The layer selection strategy is based on the significance of each layer, which is determined by the distance between the activation outputs of different transformer blocks. Formally, for a predefined number of layers to be pruned, denoted as n, the optimal cut index I** is determined by minimizing the distance between hidden states before and after the cut. I** equals argument I lie plus n. 4. We evaluated various distance metrics H using activations computed on a small calibration dataset, with the impact of the dataset explored in section 3.3.1. For each candidate cut, the distance between hidden states before and after the cut is calculated and then averaged across the calibration dataset to obtain a robust layer importance estimate. We found that the cosine distance is particularly effective in identifying nearly optimal layers for pruning. This observation aligns with findings reported in recent studies 13. In the supplementary material at 10, we present results of an exhaustive brute force layer selection, which confirm that cosine distance consistently identifies optimal or near optimal layers for removal. Additionally, we provide a comparative analysis of the L2 distance metric to further validate our choice. 2.2 linear transform estimation to compensate for the pruned transformer blocks. We leverage the same set of calibration data to compute activations directly before and after the removal point. Using these activations, we estimate an appropriate linear transformation that accurately approximates the final output of the pruned blocks. Depending on the selected criterion, this estimation can be performed using either analytical or numerical approaches, enabling precise modeling of the omitted layers. As illustrated in Fig. 1, a linear transformation is applied following the MLP and prior to the residual summation. The goal of our method is to estimate an optimal linear transformation matrix so that T** equals argument TH by T plus Y I lie plus N 5 Greek. where h corresponds to a distance function, e.g. L2 distance, cosine distance, etc. between two input tensors, and notes the optical cut index estimated using it. 4. Once the transformation matrix is estimated, the transformer blocks from e plus 1 to plus n inclusive are removed. L2 distance classical solution for 5 arises when setting h as the L2 distance and is obtained by solving a least squares LS problem. T asterisk equals argument t y t plus yi minus y plus n2. 2 equals mt I minus 1 mt I plus m minus yi. 6. For a detailed derivation of the above result, we refer to the supplementary material at 2. Cosine distance dot is discussed in section 2.1. Our ablation study on various distance functions to assess the importance of transformer blocks revealed that the cosine distance is the most effective in identifying the least significant blocks. Motivated by these results, we have further used the cosine distance as the objective function to estimate the optimal linear transformation. In this case, the optimization problem takes the form t asterisk equals argument t cos m I t plus y I li plus n equals argument t n x k equals 1 minus my k t plus y I k t li plus n k my k t plus y I k 2 li plus n k 2. 7. Where cos denotes the cosine distance between the two input vectors, we use the notation my k r d t to denote the kt each row of a matrix my r n times t, which we then represent as a column vector. Here, the cosine distance is calculated per token count aggregated over all in tokens. Unlike the L2 distance formulation, this objective does not admit a closed form solution, and thus a numerical optimization approach is required. In our experiments, we have utilized the atom-mind optimization algorithm. Furthermore, an ablation study involving various alternative numerical solvers can be found in the supplementary material at 6. To solve the optimization problem in 7, it would be necessary to store the hidden states my e and li plus n. To improve memory efficiency, we instead optimize the following simplified formulation: t asterisk equals argument t cos m I t li plus n minus yi. This alternative formulation requires us to store only my and the difference li plus n minus yi instead of keeping all three matrices. In supplementary material at 1. We empirically demonstrate that this simplification has a negligible effect on performance while improving memory efficiency. Using the linear transformation once the optimal transformation t asterisk has been estimated, our approach allows it to be incorporated into the MLP layer of the ITH transformer block. Since the learned transformation and the pre-cut MLP block represent the sequential linear operators, they can be algebraically composed into a single equivalent linear transformation, allowing t asterisk to be fused with the weight matrix of the down projection linear layer of the MLP block. Consequently, the overall architecture of the model remains unchanged, except for the removal of the non-effective transformer blocks. 2.3 Regularization. We further consider estimating the linear transformation by imposing additional constraints on the matrix T through regularization. Specifically, we reformulate the optimization problem as follows: t asterisk equals argument thm it plus yi li plus n plus alpha rt 9, where r denotes a regularizer and alpha controls its strength. To promote sparsity in the transformer, to on matrix 10 encourage a more balanced distribution of feature importance, we use both L1 and L2 regularization terms when we use the cosine distance as our objective. When we instead utilize L2 at our objective, we derive the analytical solution under L2 regularization. Empirical analysis shows that the considered regularization approaches improve the ability of the pruned model to generate accurate predictions, as reflected by the accuracy-based benchmark CSEC free, though such improvement comes at the cost of increased perplexity. 4. 2.4 Multiple linear transforms. The proposed ReplaceMe method can be easily extended to be applied on multiple non-overlapping groups of blocks within the model, estimating a separate linear transformation for each group multi-LT. This approach provides flexibility in achieving the desired performance metrics even under high compression ratios. Furthermore, if some of the selected groups of blocks are consecutive, that can be merged into a single block with one corresponding linear transformation. We refer to this method as non-consecutive multilinear transformations multi-LT and C. Experimental analysis. Further validating multi-LT and C are detailed in the appendix at 16. Free experiments. In this section, we first describe our experimental setup and then provide a systematic comparison of our training-free pruning method against existing structured pruning approaches, including those relying on healing mechanisms. In particular, we show that our method achieves competitive performance without requiring additional training. To further analyze the factors influencing our approach, we conduct ablation studies on several key aspects: the calibration dataset used for choosing the layers to be pruned and for estimating the linear transformation, the choice of distance function in EC 5, and the impact of regularization in the linear transform estimation. 3.1 Experimental setup. In our experiments, we have focused primarily on LMA2-7B and LMA3-8B instruct models, while also reporting results for QN 2.5-7B and FUCN 11B for comparative analysis. Results for additional models are provided in the supplementary material at 7. For numerical estimation of the linear transform, we used M optimizer with LR1E-4 and batch size 1024, iterating for 10 epochs over the calibration data. In Table 1, we present results on different benchmarks that have been widely used in previous research. These benchmarks have been introduced in the following works: TMNLI56, LSI57, PICA2, JIV59, WSE24, and MLU16, TMLU25, resize/middle 22, C346. Additionally, we benchmark ReplaceMe using well-established public datasets, namely WinRand 41, Bool Q4, OpenBook QA31, TyQ55, and Lambda OpenAI 35. For all benchmarks except Lambda OpenAI, we report accuracy as the evaluation metric, along with the average accuracy across all benchmarks. For Lambda OpenAI, we report perplexity to calculate the environmental impact. We use Code Carbon 6, a well-known tool to estimate CO2 emissions and power consumption. 3.2 Comparison with other structured pruning methods. In this section, we report our key findings from applying ReplaceMe across various model architectures and benchmarks. To ensure the statistical stability of our results, all experiments are executed multiple times. As demonstrated in Fig. 2, we conduct a comparative analysis between ReplaceMe and UIDL 13, evaluating key metrics including time to get a comparable accuracy, environmental impact, and final model performance. Notably, for UIDL healing process, we restricted fine-tuning to low-rank adaptation, low RA applied exclusively to the MLP layers, whereas alternative approaches incur significantly higher computational costs. Our proposed method exhibits substantially reduced computational demands and achieves a markedly faster recovery compared to other methods. In Table 1, we compare ReplaceMe with other state-of-the-art structured depth pruning approaches. It should be noted that all competing methods rely on healing mechanisms and require extensive retraining, whereas our method remains completely train-free, no healing is applied. Despite this, as shown in Table 1, our method consistently outperforms all baselines on average and achieves 92.5% of the performance of the uncompressed Llama 2-7B model at a 25% compression ratio. In Table 2, we further compare our method against state-of-the-art structured pruning approaches on the more recent Llama 3-8B instruct model under the setting where no healing is applied. We note that SED LLM53 employs a low-rank approximation of the weights, while LLMP Unit 29 combines both width and depth pruning. Despite these differences as shown in Table 2, our method again outperforms these baselines. All results are reported at a 25% compression ratio. The multi-LT results correspond to the adaptation of the method described in section 2.4, while the identification of multiple groups of blocks typically yields consecutive blocks in most cases. We additionally evaluate the scenario where non-consecutive blocks are enforced. This configuration demonstrates an improvement in complexity but leads to a performance degradation across benchmark tests. 5. Emissions time year 113.616.6107169 route to LS environmental normalized comparison. Rs LS Rs cosine UIDL Rs cosine Rs LS UIDL 859,095,192.5 89.99 relative accuracy. Figure 2. Comparison of the proposed LLM compression method with state-of-the-art UIDL subplots. Illustrate a compression time and environmental impact CO2 emissions MB performance. Accuracy relative to the uncompressed baseline. Our approach attains the shortest compression time and reduced emissions while achieving the highest accuracy, demonstrating superior efficiency, sustainability, and effectiveness over existing methods. Method train free C3C EMN legit. Test WSE health. 5 Pico race M race HMMLUC MMLU VD RP Llama 27B baseline 43.833.0 41.637.2 135.831.345.546.831.845.3 LLM streamline asterisk 43.33.024.136.561.172.535.837.045.549.441.692.0% LLM puner asterisk 29.73.428.440.692.022.0.25.3 Slice GPT asterisk 31.531.618.543.347.027.028.28.824.835.177.5% Echo asterisk 39.73.4.46.140.455.769.823.622.626.525.237.482.7% Udal asterisk 40.23.4.41.540.035.234.744.628.940.990.3% Ars cosine 42.533.025.238.559.431.135.436.746.430.441.992.5% Ars ls 39.433.018.938.558.537.136.545.229.240.789.9%. Table 1. Comparing other pruning methods after healing and our training free approach ReplaceMe. Asterisk indicates that the numbers are taken from streamlined paper 3. After compressing Llama 2.7b with 25% compression ratio signifies that the model was trained following pruning, whereas indicates that the model is training free. We also report the relative performance to the original unpruned model RP. In figure 3, we also compare our training free approach ReplaceMe against UDL 13 across various models and different amounts of layer pruning. Our method consistently outperforms UDL in both benchmark scores and complexity evaluations, while also exhibiting greater stability. Finally, we note that at high compression ratios, applying a healing process becomes necessary, as linear transformations alone are insufficient to fully recover performance. Details are provided in table 3. Although ReplaceMe continues to outperform UDL under these conditions, a healing phase is required at extreme compression levels to maintain model effectiveness. 3.3 Analysis. Up to this point, we have outlined our primary goal, replacing a series of transformer blocks with a simpler estimated linear transformation using calibration data. The nature of this calibration data is critical, as we demonstrated in section 3.3.1, where the type of fixed instructional VS plane and the amount of data significantly influence our results. Furthermore, in section 3.3.2, we analyze the impact of regularization on results, revealing a trade-off between performance metrics such as complexity and accuracy. In the supplementary material, we further explore structured linear transformations, for example, diagonal or orthonormal matrices. 3.3.1 Ablation on calibration data. Our pruning method eliminates the need for additional training by leveraging small calibration datasets in place of conventional training data. These calibration datasets serve two core purposes: 1. Assessing block importance to identify transformer blocks for removal section 2.1, and 2. Capturing hidden states before and after the pruned blocks to solve the optimization problem in EC 5, which leads to the estimated linear transformation. The quality and characteristics of these calibration subsets are critical to the accuracy of the estimation. To understand the influence of calibration data, we conducted ablation studies exploring the impact of sample size and dataset type, including plain text, instruction tuned data, and self-generated content. Our primary experiments utilized datasets such as RC5, FineWeb36, and SlimOrca26, consistent with prior work like UDL 13. 6. Method linear transform Lambda OpenAI PPL down arrow AVG EC up arrow RP up arrow Llama 3 AP instruct 3.110.7 100% SVD LLM 53 and 29.90 0.59 85.3% LLM Puna 29 and 12.31 0.60 85.3% UDL 13 Identity 2216.96 0.58 82.5% ReplaceMe Ars linear LS 20.23 0.63 89.9% ReplaceMe Ars linear cosine 15.88 0.63 90.9% ReplaceMe Ars multi LT NZ cosine 13.95 0.639 0.0%. Table 2. Results of pruning Llama 3 AP instruct for 25% using different methods without any healing or fine-tuning. AVG EC is the average performance across the race whenever Pika Bool Q Open Book QA and Sci-Q benchmarks. Perplexity is measured on the Lambda OpenAI dataset. We also report the performance relative to the original unpruned model RP. Multi-LTNC denotes that non-consecutive blocks case when applying the method described in section 2.4. 2460.550.60.650.7 accuracy Llama 3 AP instruct. UDL ReplaceMe Atom 0 510 150.550.60.650.7 Falcon 2 11B 2460.550.60.650.7 Q1 2.57B instruct. Figure 3. Comparison between our method and UDL with different number of pruned layers and different models including Llama 3 AP, Mistel 37B, and Q1 2.57B. We show the average accuracy across the race whenever Pika Bool Q Open Book QA and Sci-Q benchmarks. In particular, we investigated 3 key factors. 1. The effective dataset type and its source. 2. The minimum amount of data required to produce stable and accurate estimates. And 3. The efficacy of Messing as a lightweight data augmentation strategy when working with limited calibration samples. As shown in table 4, we apply our method to prune LMA3 AP8 by 25% using ReplaceMe. Across all ablation settings, we evaluate 3 distinct calibration datasets: FineWeb, a plain text, web corpus, SlimOrca, a curated instruction dataset generated with ChatGPT, and Orca generated a synthetic dataset where responses are generated by the baseline model targeted for pruning using prompts from SlimOrca. Impact of calibration dataset type is shown in table 4. Calibration with instruction datasets leads to better performance on benchmark evaluations than using plain text, particularly for instruction tuned models. While self-generated data yields improved perplexity scores, it tends to underperform on downstream benchmarks. This observation is consistent for both the optimization objectives that we utilize in EC 5, that is the L2 and cosine distances. We have also explored combining SlimOrca with other datasets such as FineWeb and Dive43. The latter is a multilingual corpus covering 66 languages. Interestingly, these mixed datasets perform on par with SlimOrca, suggesting that high-quality instruction data have the biggest impact. Furthermore, in the supplementary materials section at .12, we present a comprehensive analysis of the impact of calibration dataset size, including the minimum number of samples required to achieve stable model performance. We also introduce a messing-based augmentation technique designed to compression ratio of 12.5%, 25%, 37.5%, 50%, UDL 59.9, 50.4, 41, 30.4, R 64.6, 60.7, 51, 38.6. Table 3. Average accuracy for our method and UDL at high compression ratios is compared across the race whenever Pika Bool Q Open Book QA and Sci-Q benchmarks. 7. Method objective calibration data AVG EC up arrow perplexity down percent up baseline model 0.7 3.11 100.0 ReplaceMe LS FineWeb AK 0.56 26.74 80.47 ReplaceMe LS SlimOrca AK 0.622 1.21 89.59 ReplaceMe LS Orca generated AK 0.611 3.58 87.40 ReplaceMe cosine FineWeb AK 0.58 25.07 83.16 ReplaceMe cosine SlimOrca AK 0.63 15.90 90.67 ReplaceMe cosine 4K SlimOrca plus 4K FineWeb 0.63 15.85 90.51 ReplaceMe cosine Nix of 66 languages 0.63 15.72 90.64 ReplaceMe cosine Orca generated AK 0.611 3.24 87 0.33. Table 4. Pruning results for Llama 3 AP instruct user ReplaceMe 25%. We estimate the linear transformation using different data, including plain text data such as FIMAB36 and self-generated data using some Orca instructions. Maintain robust performance even when only a limited subset of data samples is available, ensuring computational efficiency under resource-constrained conditions. In addition, section 10.17 presents results with task-specific calibration datasets, showing that using data from the same task has an evaluation target, e.g., SciQ further improves accuracy compared to general-purpose calibration data, such as some Orca. 3.3.2 Regularization effect. We have also investigated how regularization impacts the linear transform estimation. We have applied ridge regularization for the L2 objective and observed that for 0 alpha 103 and 9 we notice a slight improvement in complexity, while the average accuracy on benchmarks remains the same. Conversely, increasing alpha further to 104 tends to enhance benchmark accuracy, though at the cost of higher complexity. Thus, one can consider alpha as a trade-off parameter between complexity and accuracy of the pruned model. Regarding the cosine distance objective, L1 regularization with alpha equals 10-4 gives a higher boost to accuracy at the cost of complexity performance. Similar results we obtained for L2 regularization, but compared to L1 regularization, the performance gain on benchmarks is smaller. Model method alpha AVG at complexity RP Llama 3 AP 0.6973.1100.0. ReplaceMe LS 0.624 21.289.6. ReplaceMe LS plus L2 reg 0.10.625 21.289.6. ReplaceMe LS plus L2 reg 0.50.625 21.289.6. ReplaceMe LS plus L2 reg 10 0.624 21.289.5. ReplaceMe LS plus L2 reg 100 0.624 21.189.6. ReplaceMe LS plus L2 reg 1000 0.624 20.889.5. ReplaceMe LS plus L2 reg 100,000.6262 2.989.8. ReplaceMe cosine 0.63415.990.9. ReplaceMe cosine plus L2 reg 0.010.635 20.791.1. ReplaceMe cosine plus L1 reg 1 times 10 minus 40.63822.19 Table 5. The effect of regularization on LS and cosine methods in terms of accuracy and perplexity. 3.4 Vision transformers pruning. So far, we have focused on the application of ReplaceMe exclusively to the decoder transformer architecture, specifically within LLMs. This raises an important question. How well does this method generalize to other tasks beyond text generation, particularly when the transformer acts as an encoder? To answer this, we have applied ReplaceMe on the clip model for compression ratios of 13% and 25%. We utilized 8,000 samples from the Minute dataset, and using the same evaluation procedure as in 37, we considered well-known benchmarks, namely MSOCO 27, CIFAR 1021, EuroTAP 15, BTAP 58, and Pascal VOZ 2.79. For comparison purposes with a state-of-the-art method, we also report results when UIDL 13 is applied on the same model. 8. Model compress ratio MS Coco captions retrieval CIFAR 10 0 shot VOZ 2007 multilabel 0 shot V tab site fluto SET text recall at 5 vision recall at 5 ac 1 ac 5 main AVGP ac 1 ac 5 clip L slash 1437 0.794 0.611 0.9560 0.9960 0.790 0.625 0.960 UIDL 13% 0.745 0.609 0.927 0.9960 0.781 0.490 0.931 replace me LS 13% 0.767 0.62 0.939 0.996 0.80 0.552 0.941 UIDL 25% 0.515 0.418 0.693 0.971 0.597 0.381 0.814 replace me LS 25% 0.556 0.471 0.780 0.971 0.688 0.395 0.823 Table 6 Pruning clip vision encoder user replace me. The model performance after compressing by 13% is almost as good as the original one, while in both scenarios our method outperforms UIDL. As shown in Table 6, replace me retains a strong performance on clip IT 37 even at a 13% compression ratio, closely matching the original model's accuracy and without requiring any additional training. While performance declines at higher compression ratios, this degradation is expected and consistent across benchmarks. Despite this, replace me consistently outperforms the training-free state-of-the-art method UIDL 13. Finally, we note that the performance can be further improved by utilizing a lightweight post-pruning healing procedure. For related work, model pruning 2314 has been at the frontier of deep learning research since the early developments of this field. It has found practical applications not only in model size reduction, but also in enhancing the interpretability of the models under study. Earlier studies on transformer-based language models, such as BERT, demonstrated that these models are highly compressible 4240. The same observation holds for pruning LLMs. A significant number of studies focuses on unstructured pruning, where individual weights within matrices throughout the model are zeroed out, resulting in sparse connections. Sparse GPT-11 tackles the challenge of layer-wise reconstruction and pruning by leveraging approximations of an intersection matrix. 1-47 improves the sparse GPT idea of reducing computations via simplification of the Hessian approximation. The LLM Surgeon 52 uses Kroneck curvature approximations to perform pruning of LLMs. Despite maintaining high model quality post-pruning, computational savings from unstructured pruning requires specialized hardware support for sparse computations, limiting its wide applicability. In contrast, structured pruning involves the complete elimination of certain structures inside the network. In this context, removing entire attention heads or MLP channels is referred to as width pruning. LLM Unit 29 suggested to calculate an importance metric based on the difference in the loss when this is computed with and without a pruned group of weights, respectively. FLAP 1 proposed a training-free approach that is based on a fluctuation pruning metric and an adaptive compression ratio. Another typical strategy within structured pruning is depth pruning. Methods in this category remove entire transformer layers of the network. In shortened Llama 18, the author suggested identifying the significance of each decoder layer using complexity analysis and a Taylor metric. This metric is based on a similar idea with the LLM Unit importance metric. That is, it measures the difference of the model loss when computed with and without a pruned layer. After pruning, the authors 18 further proposed healing via low RA fine-tuning, continual pre-training, or their combination. The authors of short GPT-30 introduced the block influence BI metric to quantify the contribution of each network layer. This metric corresponds to the cosine distance between the hidden states before and after the layer. After pruning, they optionally recommend retraining the model to recover the model's performance. In contrast, UIDL 13 suggested computing the importance of a fixed length sequence of layers instead of computing this metric for each layer individually. They calculate the cosine distance between the input and the output of the sequence, and then if the distance is below a predefined threshold, they remove the entire sequence of layers completely. Post-removal healing with low RA on the MLP is applied. In the recent LLM Streamline paper tree, the authors proposed to replace a fixed length sequence of layers with a lightweight network, which can be either a transformer, layer, or a feed-forward network if FN. This network is then trained using the MSE loss and the LLM loss with low RA. Prior work 38 has demonstrated that certain transformer blocks exhibit 9 linear characteristics with empirical analyzers revealing near perfect linear relationships between embedding transformations across layers. They suggest to substitute highly linear transformer blocks with linear layers, which facilitates efficient model compression through direct knowledge distillation. Furthermore, the study proposes incorporating a cosine similarity-based regularization mechanism during pre-training to mitigate excessive linearity. Recently, the Minitron LLM family 33 and its pruned variants were introduced, demonstrating an effective balance between depth and width pruning. To mitigate performance degradation, the approach estimates the relative importance of depth and width dimensions to achieve an optimal trade-off that minimizes performance loss. However, a notable drawback is its reliance on a substantial amount of data, approximately 100 B tokens. 5 limitations. While the effectiveness of our proposed method is mathematically justified and experimentally validated, it is important to note that due to the training-free nature of ReplaceMe, such effectiveness is primarily evident within certain certain compression ratio ranges. As demonstrated in Figure 3, ReplaceMe performs well without fine-tuning for what we refer to as reasonable compression ratios, which are dependent on both the size and architecture of the original model. For higher compression ratios, some degree of retraining or parameter adjustment becomes necessary. However, an advantage of our approach is that such fine-tuning can be limited to only the linear transformation, rather than requiring full model fine-tuning. This selective healing preserves the computational efficiency of our method, as further detailed in the supplementary material, and contributes to its overall efficiency compared to alternative approaches. 6. Conclusion. In this work, we introduced a novel method named ReplaceMe, which is a train-free depth pruning method. Our proposed strategy involves substituting certain transformer blocks with a linear transform, which is estimated using calibration data. ReplaceMe requires no retraining or fine-tuning, yet it consistently outperforms existing pruning techniques in train-free settings and remains competitive even when compared to approaches that rely on post-pruning healing stages. We have conducted extensive experiments and outlined methodologies to accurately estimate linear transformations under different optimality criteria using both analytical and numerical techniques. The proposed method has been evaluated across a range of transformer architectures, including large language models and vision transformers, demonstrating its robustness, adaptability, and effectiveness. These results represent a significant step toward a truly train-free pruning strategy. References: Wan Yanqi and Zhu Zhao, Tao Yu, Mingtang, and Jiqiao Wang. Fluctuation-based adaptive structure pruning for large language models. In proceedings of the 38th Conference on Artificial Intelligence and 36th Conference on Innovative Applications of Artificial Intelligence and 14th Symposium on Educational Advances in Artificial Intelligence. Press 2024. Tu Yan and Bisk, Ruan Zos, Ronan Labras, Jean Feng Gao, and Yejin Choi. Pickup Reasoning about Physical Common Sense and Natural Language. AI Conference on Artificial Intelligence 2019. 3 Zhao Dongchen, Yuxuan Hu, Jingjing, Enling Wang, Kueting Lai, and Han Chen. Streamlining redundant layers to compress large language models. And the 13th International Conference on Learning Representations 2025. 4 Christopher Clark, Kenton Lee, Ming Wai Ching, Tom Kwai Kasi, Michael Collins, and Christina Taranova. Exploring the surprising difficulty of natural yes/no questions. In proceedings of the 2019 Conference of the North American Chapter of the Association for Computational Linguistics, Human Language Technologies, Knuckle HLP 2019, Minneapolis, MN, USA, June 2-7, 2019, Volume 1 Long and Short Papers, pages 2924, 2936, Association for Computational Linguistics 2019, 10. 5 Peter Clark, Isaac Kai, Warren Ethani, Tasharkot, Ajisa Barrel, Gorza Sonic, and Oyvind Teftor. Thank you have solved question answering. Try ARC, the AI 2 reason. Challenge.ru for print RU colon 8 and 3.05457 2018. 16 Macordi, Victor Schmidt, Lucioni, Goyle Camel, Marion Cotto, Boris Feld, J. Vanny Licord, Liam Connell, Amin Zaboni, Ines Tupatomic, Matha Label, Louis Blanche, Alexis Kruveller, Amanazara, Franklin Zhao, Adida Joshi, Alexis Bagra, Hughes Stola, Foray, Nico Lasaris, Eduardo Avati, Douglas Blank, Zia Wang, Armin Katavik, Mark, Lincoln Mickelson, Etchley, Christian Bauer, Lucas Otavio, and Arajo, JPW, and Minerva Books. MLCO 2/code carbon. E2.4.1, 2024. Set and Alexi Dosovitsky, Lucas Baer, Alexander Kolsenkov, Dirk Weisenborn, Theo Huajai, Thomas and Terther, Mustafa Dedani, Matthias Minder, Georg Heigl, Sylvain J. Ekobus Foray, and Neil Halsey, and images were 16 words. Transformers for image recognition at scale. International Conference on Learning Representations 2021. Ada Femini Huduvi, Apina Jari, Apina Fandi, Apina Kadian, Ahmed Aldal, Age 11, Ekel Mether, Alan Chilton, Amy Yan, Angela Fen, Anurag Gwil, Anthony, Hartshorn, Elbo Yan, Archie Mitra, Archie S. Kumar, Arden Kornif, Arthur Hinsark, Aaron Rao, Sanjing, Aurelian Rodriguez, Austin Gregerson, Ava Sadaru, Baptiste Rosier, Bethany Byron, Bintang, Body Churn, Charlotte Kachiku, Tianeg, Chloe Bai, Chris Merritt, Chris McConnell, Christian Keller, Christopher Turret, Tanyan Wu, Green, 1, Christian Canton Furrer, Cyrus Nicolaides, Damien Onzis, Daniel Son, Daniel Pins, Danny Legits, David Easyolbu, D.H. of Chowdhury, D.H. of Majan, Diego Garcia Olano, Diego Perino, Dio Cups, Igor Latkin, Ab Albadai, Lena Lobanova, Emily Dinnan, Eric Michael Smith, Philip Radanovic, Frank Chang, Gabriel Sinev, Gabrielle Lee, Georgia Louis Anderson, Graham Mail, Gregoire Milan, Guan Peng, Dylan Tukuro, Haley Nguyen, Anna Korvar, Huzu, Hugo Tuvran, Ilian Zerov, Emmanuel Rieta Iba, Isabel M. Plowman, Ishin Misra, Ivan Evimov, Jake Covet, Ewan Lee, Jen Jeffer, Jonathan Brains, Jason Park, Jay Mahedakar, Ji Cha, Jelmer Vanderlind, Jennifer Billick, Jenny Han, Jenny Lee, Jeremy Fu, Jan Finkai, Jenny Wan, Joe and Liu, Jay Wing, Jago Yu, Joanna Bitten, Joe Spisak, Johnson Park, Joseph Rocca, Joshua Johnson, Joshua Sex, Chinten, Gia Kaleon, Vesidinola, Kartik Yupasai, Kate Poyak, Gila, Kenneth Hefield, Kevin Stone, and Adele. The Llama 3 Herd of Models.co RR, Abslish 24, Fit 7.21783, 2024. 9 Mark Everingham, Luke Van Gool, Christopher K.I. Williams, John Wynn, and Andrew Zisman. The Pestle Visual Object Classes Vok Challenge. International Journal of Computer Vision 88, 303, 338, 2010. 10 Clementine Foyer, Ethan Haddad, Elena Lazasaya, Conrad Schaefer, and Thomas Wolf. Open LLM Leaderboard V2 https://hidingface.co/stasis/open LLM Leaderboard /open LLM Leaderboard 2024. 11 Elias Frater and Dan Alisar. Sparsift. Massive language models can be accurately pruned in one shot. International Conference on Machine Learning Eichel 2023. 23-29 July 2023. Honolulu, Hawaii, USA. Pages 10,323, 10,337. PMLR 2023. 12 Leo Gao, Jonathan To, Sal Biderman, Sid Black, Anthony Dipovi, Charles Foster, Lawrence Golding, Jeffrey HSU, Kyle Donald, Nicholas Muanayoff, Jason Feng, Larry Reynolds, Eric Ten, Ashside, Ben Wang, Kevin Wang, and Andy Zhu. A framework for few-shot language model evaluation 2021. 30 Andrew Guama, Kashal Terumala, Asan Chavrian, Paolo Goyoso, and Daniel A. Roberts. The unreasonable ineffectiveness of the deeper layers.co RR. Absolute 24, 3.17887, 2024. 14 Songhan, Jeff Poole, John Tran, and William Daly. Learning both weights and connections for efficient neural network. Advances in neural information processing systems. Current Associates Inc. 2015. 15 Patrick Calvert, Benjamin Bish, Andreas Dengel, and Damien Borth. Euroset, a novel dataset and deep learning benchmark for land use and land cover classification. IEDE journal. Of selected topics in applied Earth observations and remote sensing. Clause 7:2217, 2226, 2019. 11. 16 Dan Hendricks, Colin Burns, Stephen Bazart, Andy Zhu, Matis Mazica, Donson, and Jacob Steinhardt. Measuring massive multitask language understanding. RZIF for print. RZIF 209.033 year 2020. 17 Dan Hendricks, Colin Burns, Sora Kadavath, Ekal Arat, Stephen Bazart, Eric Kang, Donson, and Jacob Steinhardt. Measuring mathematical problem solving with a math dataset. 2021. 18 Bokun Kim, Jimin Kim, Tiho Kim, Thibault Kazos, Shinko Choi, Jin Hoshin, and Hyun Kayusal. Jordan Tella M. A simple depth pruning for large language models. 2024. 19 D Direct Key Kingnut and Jimmy Ba. M. A method for stochastic optimization. RZIF for print. RZIF 24 from 12.6980 2014. 27 Kornblith, Mohammed Norzi, Hondagli, and Jeffrey Hinton. Similarity of neural network representations revisited 2019. 21 Alex Krzyzewski, Ben on Nair, and Jeffrey Hinton. Sephard 10 Canadian Institute for Advanced Research. 22 Google Kunlai Kizak, XL Liu, Yanning Yan, and Edouard H. Helvey, Race, Large Scale, Reading Comprehension Dataset from Examinations, and Proceedings of the 2017 Conference on Empirical Methods in Natural Language Processing, EML 2017, Copenhagen, Denmark, September 9-11, 2017, pages 785, 794. Association for Computational Linguistics 2017. 23 Jan LeCun, John Denker, and Sarah Saw, Optimal Brain Damage, and Advances in Neural Information Processing Systems, Morton Kaufman, 1989. 24 Hector Levis, Ernest Davis, and Lyra Moore-Desner, The Winograd Schema Challenge, and 13th International Conference on the Principles of Knowledge Representation and Reason, 2012. 25 Heon and Lai, Ichonjing, Vajikoto, Vevayon, Haijao, Yangong, Mandarin, and Timothy Baldwin. CMMLU, Measuring Massive Multitask Language Understanding in Chinese. RU for print, RU colon 29306.09212, 2023. 26 Wayne Lion, Guan Wing, Blaze Goodson, Eugene Pentland, Austin Cook, Championship B on, and Technium. Samorka, an open dataset of GPT-4 augmented Flam reasoning traces with verification 2023. 27 Sun Yilin, Michael Mayer, George Belangi, James Hayes, Pietro Perona, Eva Raman, Peter Pilar, and C. Lawrence Sidnick. Microsoft Cocoa, Common Objects in Context, in Computer Vision F 2014. 13th European Conference, Zurich, Switzerland, September 6-12, 2014. Proceedings, Part B13, pages 747 and 55. Sprayer 2014. 28 Duncy, Liu and Jorge Nussel. On a limited memory BFGS method for large-scale optimization. Mathematical programming. 45 Wolf Recall of 1988, 1989, 29 Zhang and Ma, Offenfeng, and Xin Xiaowing. LLM Pruner on the structural pruning of large language models. Advances in Neural Information Processing Systems 36. Annual Conference on Neural Information Processing Systems 2023, NeurIPS 2023, New Orleans, LA, USA, December 10-16, 2023, 2023. 30 Zinmen, Minjitu Zhu, King Yuzheng, Bingning Wang, Hani Lulin, Yao Jilu, Dan Taihan, and Wei Pinchen. Short, layers in large language models are more redundant than you expect. RZIF for print, RZIF 224, 3.03853, 2024. 31 Toter Miel of Peter Clark, Tashar Kot, and Ashish Sabawal. Kanasuit of Armor Conduct, Electricity, a new dataset for open book question answering, and proceedings of the 2018 Conference on Empirical Methods in Natural Language Processing, Brussels, Belgium, October 31, November 4, 2018, pages 2381 to 2391. Association for Computational Linguistics 2018, 12. 32 RES, Morgos Mathuravu, and Sandy Bangyo, Insights on Representational Similarity in Neural Networks with Canonical Correlation 2018. 33 Soav Muralidan, Jeff Cheruvika, Efridinovis, Beverage Joshi, Marcin Chichasi, Mustafa Pawari, Mohamed Chuibai, Brian Karanzao, John Kotz, and Pavlo Molchanov. Compact Language Models via Pruning and Knowledge Distillation.co.r, M/2407.14679, 2024. 34 Jorge Nosel and Stephen J. Wright. Numerical Optimization, Fraynard, New York, NY2, edition 2006. 35 Dennis Paperno, German Grasusti, Angeliki Lazaridu, Quan Dokfem, Bata Brady, Sandro Pazil, Marco Bowie, Gemma Bolda, and Rafael Fernandez. The Lambada Dataset, 2016. 36 Gilmer Benito, Ina Kidley Letter to C7 Alba Ben Al, Anton Lashkov, Margaret Mitchell, Colin Raffel, Leandro Vionware, and Thomas Wolf. The final datasets, Ecanting the web for the finest text data at sale.rz for print RZ 2004 6.17557 2024. 37 Alec Rever, John Woodkim, Chris Halsey, Adi Aramish, Abriel Gope, Tantini Agar, Well, Dear Sestut, Amanda Essel, Kamala Miskin, Jack Clark, Gretchen Gruger, and Delia Setzer. Learning transferable visual models from natural language supervision and proceedings of the 38th International Conference on Machine Learning. Pages 8,748, 8,763. The MLR 2021. 38 Anton Radiv, Matej Mikulchuk, Elizaveta Goncharova, Nikolai Gerasimko, Ivan Osadits, Denis Dimitrov, and Andrew Kuznetsov. Your transformer is secretly linear. In Pro, proceedings of the 62nd Annual Meeting of the Association for Computational Linguistics Volume 1. On papers, pages 576, 584, Bangkok, Thailand, 2024. Association for Computational Linguistics. 39 David Rain, Betty Laihu, Sai Cooper Strickland, Jet Pei, Richard Yuan Peng, Julian Durrani, Julian Michael, and Sanular Bowman, JP Kuwait, a graduate level Google Proof Q&A. Benchmark 2023. 40 Yuxin Ren, Benyu Wang, Liven Xing, Din Dion, and Quinn Liu. Exploring Extreme Parameter Compression for Pre-trained Language Models 2022. 41 K6 Sakarechi, Ronan Labras, Chandra Badavachla, and Yejin Choi, Webrand, and Everserial Webrand SEMA Challenge at sale.com. Atom 64.9:99.116 2021. 42 Victor Sen, Lysander Debut, Julian Drummond, and Thomas Wolf. Istilbert, a distilled version of Vert, smaller, faster, cheaper, and lighter 2020. 43 Shivalika Singh, Freddie Vargas, Daniel D'Souza, Burjeff, Carson, Adanea Mandarin, Wayanko, Karam Chandalia, Jay Patel, David Matizunas, Laura Omani, Mike Jang, Arth Hacherachi, Joseph Wilson, Marina Machado, Yusa Suzumara, Dominic, K. Arzani, Insak, Hakamai Fadi, I. Ragun, Avon Oko, Isha Lajib, Ocean Mudaneg, Thade IFE, Bu Minching, Sebastian Ruder, Zaria Gafkonda Nade, Avemi, Sebastian Jamin, Nikos Munayoff, Max Bartolo, Julia Kreuzer, Amit Ustin, Mars, Fedi, and Sarah Hooker. I Dataset, an open access collection for multilingual instruction tuning 2024. 44 Zinsray, Zai, Ketch Bostrom, Torat Shohui, and Greg Durrett. Mother, testing the limits of chain of thought with multisets of reasoning 2024. 45 Tron Stay Hub, the conjugate gradient method and trust regions in large scale optimization. Science Journal on Numerical Analysis, 23:16, 26:16, 37, 1983. 46 Kaisan, Dian Yu, Dan Yu, and Claire Carty, investigating prior knowledge for challenging Chinese machine reading comprehension. Transactions of the Association for Computational Linguistics 8:1:41:55 2013. 47 Minji-san, Chuan Liu, Anna Bear, and J. Dico Golder, a simple and effective pruning approach for large language models in the 12th International Conference on Learning. Representations, Eichler 2024, Vienna, Austria, May 7-11, 2024. OpenReview.net, 2024. 48 Kaisan, Eduardo Zedin, and Eugen Tang, Transformer Squared, Self-Adaptive LLMS, 2025. 49 Kaisan, Mark Pickett, Akash Kumar Nain, and Leon Jones, Transformer Layers Tenders, 2025. 50 Miyaksasan, Nathan Seals, Adeneo Shelley, Sebastian Jamin, Ite, Hayam Wan, Shan, Atencha Chaudhary, Kwakvi, Layad H, Kai Deju, and Jason Y. Shalin, Big Bench Test, and What a Chain of Thought Can Solve Them, 2022. 51S, Yumiyama, Least Squares Estimation of Transformation Parameters between 2-point bands, IEE Transactions on Pattern Analysis and Machine Intelligence, 13:4:376 1991. 52 Tycho F. Avender Adara, Marcus Nagel, Mark Van Ballen, and Timon Blankenborg, the LLM Surgeon, in the 12th International Conference on Learning Representations, Ether 2024, Vienna, Austria, May 7-11, 2024. OpenReview.net, 2024. 53 Zimwang, Eugene, Donwewen, and Maijin, FEDLLM, Truncation Aware Singular, Value Decomposition for Large Language Model Compression, in the 13th International Conference on Learning Representations 2025. 54 Yuba Wayne, Zubon Ma, Dijing, Yuan Chengnai, Vrana Chandra, Jibon Guo, Wanning Ren, Aran Arrowhead, Juan He, Dian Jiang, Channel Light, Metku, Kai Wang, Alex Tuang, Rocky Fan, Zhenyu, and Wenu Chen, MMLU Pro, a more robust and challenging multitask language understanding benchmark 2024. 55 Johans Webble, Nathan F. Leo, and Matt Gardner, crowdsourcing multiple choice science. Questions in proceedings of the third workshop on noisy user-generated text. Edit M. 2017, Copenhagen, Denmark, September 7, 2017, pages 94-106. Association for Computational Linguistics 2017. 56 Lanzhu, Haihu, Juan Leijing, Lu Lai, Chen Jikao, Yudong Lai, Yechenzu, Kaisan, Dan, Yukon Yu et al. Plu, Chinese Language Understanding Evaluation Benchmark.rziv, preprint RUF colon 24.05986 2020. 57 Rowan Zellers, Ari Holtzman, Yan and Bis, Ali Farhadi, and Yejin Choi. Helfwed, Kane, Ching really finish your sentence RUF preprint RUF colon 19.07830 2019. 58 Seo Huijai, Joan Puitzer, Alexander Kolsakov, Pierre Resin, Carlos Ricconi, Mario, Lucic, Joseph Chalanda, Andre Zuzano Pinto, Matan Newman, Alexei Dosovitz et al. A large-scale study of representation learning with a visual task adaptation benchmark.rziv, preprint RUF colon 19.10.48667 2019. 59 Chu Jijing, Minli Huan, and 8 Sun Chid, a large-scale Chinese idiom dataset for closed test.rziv, preprint RUF colon 19.6.01265 2019. 14 Appendix. In this section, we revisit the central aspects of our research, starting with the closed form solution presented in Addend 2. This provides a foundation for examining structured linear transformations LTSS discussed in Addend 3, leading to key experimental findings. We evaluate multiple numerical solvers to minimize the cosine objective of Addend 6 and investigate the behavior of structured LTs. We then assess the applicability of our method on diverse model architectures, demonstrating the effectively applied healing process on the proposed ReplaceMe. In addition, we include a computational comparison between ReplaceMe and competing approaches, as those introduced in our initial study. Further, we dissect the role of integrating a linear layer as a standalone block between full layer activations. This is in contrast to our approach of merging LTs with MLP activation into primary architecture. The obtained results reveal that both methods yield remarkably similar results. Finally, to validate the robustness and generalization ability of our method, we evaluate several models on a wide range of benchmarks. These experiments demonstrate the stability and adaptivity of our approach in varying conditions. Addend 1 terminology and definitions. Relative performance (RP), a normalized metric quantifying performance relative to the baseline model, computed as the ratio of benchmark results between the evaluated model and the baseline. Compression ratio, the proportional reduction in model parameters expressed as a percent. Age calculated as 1 minus n prune. Original times 110, where n pruned and original represent the number of parameters in the compressed and original models respectively. ReplaceMe, our proposed method for model compression, which replaces complete transformer blocks with optimized linear transformations. Average accuracy (AVG) the arithmetic mean of model accuracy scores across multiple benchmark datasets. Perplexity, a metric for evaluating language model performance, defined as the exponential of the cross entropy loss on the Lambato Benai benchmark. Addend 2 closed form solution for L2 distance. The optimization problem for the linear transform matrix estimation can be expressed as follows: T asterisk equals argmin T by T plus yi minus li plus n2. 2. The objective is an Euclidean norm, and thus we can extend it to R2. 2 equals TR my T plus yi minus li plus n my T plus yi minus li plus n. 11 equals TR Tm I my T plus 2 yi minus li plus n my T plus L I plus n li plus n. To minimize the objective, we take the gradient with respect to 10 set it to 0. TR2 2 equals 0 12 2m I my T plus 2m I minus li plus n equals 0 m I my T equals m I li plus n minus yi T asterisk equals m I my minus 1 m I li plus n minus yi 15. Addend 3 structure LT matrix. To improve the interpretability of our approach, we further investigate additional constraints that can be imposed on the structure of the linear transformation T. The results of all the different constrained transformations are presented in Addend 4, motivated by the transformer square work 48. We also consider the case where we condition T to be a diagonal matrix. This constraint is meaningful under the assumption that an adequate mapping of the activations is possible for only scaling of the hidden states. In this case, the optimization problem is of the form T asterisk equals argmin T dd times dm I T plus yi minus l I plus n2 to where d n times n denotes the space of diagonal matrices of dimensions d times d. The corresponding closed form solution is given by T asterisk equals m I my I minus 1 m I li plus n minus yi I 13, where denotes the Hadamard product. Another constraint that can be imposed onto is the requirement for it to represent an orthogonal transformation 51. T asterisk equals argmin T m I T plus yi minus l I plus n2. 2 SDTT equals I. This problem admits an analytical solution via singular value decomposition. Specifically, let FVDM I li plus n minus yi equals u sigma v. Then the optimal orthonormal matrix is given by T asterisk equals uv. Addend 4 results of structured linear transformations. Our evaluation protocol, summarized in table 7, explores constrained forms of the linear transformation matrix T r d times t, inspired by the architectural design of transformer squared 48. We first examine the case where it is restricted to a diagonal matrix I. T equals di T1 TD. Although this parameterization successfully restored model functionality, the resulting perplexity P remains suboptimal with P di P generic, where P generic represents the baseline achieved using a constrained full matrix. Model LT structure multilinear transform AVD aparo perplexity down percent up. Llama 3 8 B 0.7 3.11 100.0 Udal 0.58 2216.96 ReplaceMe generic 0.62 21.21 89.59 ReplaceMe orthonormal 0.60 700.57 85.67 ReplaceMe diagonal 0.62 89.09 88.42 ReplaceMe generic non-consecutive 0.6216.07 89.60 Table 7 Relation study on non-constrained LT matrix structure generic diagonal rotational and multilinear transforms. The base model is set to Llama 3 8B with 25% pruning ratio. Subsequent experiments with orthogonal transformations T where TT equals I demonstrated limited efficacy, yielding only marginal performance recovery. This indicates that actual scaling is much more important to recover model performance than rotations or reflections. More promising results emerge from employing multiple linear transformations type K. I equals 1. We examined the following approach: non-consecutive transformations for disjoint parameter subsets. We learned independent transformations C disjoint I equals 1. The experimental results indicate that applying multiple transformations yields consistent improvements in both perplexity P and accuracy across both analytical and numerical solutions. For the analytical approach, these gains are achieved in a single computation step, whereas the numerical solution requires iterative optimization, leading to significantly higher computational costs. 16. Addend 5 statistical significance. To ensure reproducibility and stability of our method, we ran our method multiple times for Llama 3-8B and struck with a pruned layers. While the analytical solution always leads to the same results, numerical methods might have different results. However, we were able to get almost the same results. 1. The mean average accuracy over all benchmarks equals to 60.71 and the standard deviation STD is 0.08. 2. The mean Lambato Benai perplexity equals to 50.90 and the standard deviation STD is 0.05. Addend 6 comparative analysis on the performance of numerical solvers. This section investigates the effects of different optimization solvers when minimizing a cosine distance objective function. The previously reported results were obtained using the Atom optimizer. Here, we perform a systematic comparison using alternative solvers including 1 nonlinear conjugate gradient NLCG, Newton's EG, and limited memory BFG SLBFGS. Additionally, we compare the results obtained when minimizing the mean squared error MSE either via numerical optimization or using the least squares LS closed form solution. These comparisons provide insights about the solver efficiency and the solution accuracy for different objective functions. The solver AVG RP percentage baseline 9 0.697 3.106 AM 19 0.634 15.875 90.94 yo NLCG 34 0.630 15.960 90.412 LBFG best 28 0.634 16.2 EM 90.921 Trustin CG 45 0.62 47.2 88.945 LS 0.624 21.2 689.588 MSE plus Atom 0.624 20.633 89.536 Table 8 comparison between different solvers to estimate the linear transform for Llama 3 8B after 25% compression with cosine distance objective and a sanity check between MSE with Atom solver as a numerical solution and a less analytical solution demonstrated in Table 8. Nearly all solvers converge to a similar point, with results on both benchmarks and complexity metrics being very close. An exception is the Trustin TG solver, which seems to got trapped in a local minimum. Furthermore, there is a clear indication that minimizing the MSE either numerically or analytically yields nearly identical outcomes. Nevertheless, the analytical solution is much faster and has much less hardware requirements. Addend 7 generalization across model scales. While the primary results presented in this work focus on a subset of model architectures, these findings may not fully capture the scaling behavior across a broader parameter spectrum, where model sizes can vary from 1 billion to 70 billion parameters or beyond. To rigorously investigate the scaling properties of our approach, approach, we conduct extensive experiments across the following benchmark suite: WinEver N41, Wool Q4, OpenBook QA31, SciQ55, Race 22, and Pika 2. Our ceiling analysis involves the Llama 3 architecture family from the compact Llama 3.21b parameters to the largest available variant, Llama 370b parameters. As evidenced in Table 9, we model Llama 3.2 DIT, 1b instruct Llama 3.1 DIT, 8b instruct Llama 3 DIT, 70b instruct, baseline ReplaceMe, baseline ReplaceMe, baseline ReplaceMe, ReplaceMe, AVD NAC 0.6098, 0.548, 0.7118, 0.6537, 0.7280, 0.7036, 0.6596, RP 1.8, 0.8771, 1.8, 0.9184, 1.8, 0.9664, 0.960. Compression ratio 0%, 25%, 0%, 25%, 0%, 25%, 37.5%. Table 9. Results of utilizing ReplaceMe on various model sizes characterized by the number of parameters for the Llama 3 families. For Llama 3-70b instruct, we show ReplaceMe results with 25% and 37.5% compression ratios. Observe a strong correlation between model size and achievable compression ratio eta, specifically for 17. Large-scale model 70b parameters, we achieve optimal compression ratios of eta max equals 37.5% while maintaining performance retention RP greater or equal to 90% of the original model's capability. Adaptive computational efficiency analysis. This section presents a quantitative comparison between our training-free method and the baseline UDL framework with a focus on computational overhead, energy consumption, and associated CO2 emissions. As demonstrated in the Table 1, our approach achieves competitive performance despite being training-free, whereas UDL requires fine-tuning on a limited dataset. To ensure an equitable comparison, we adopt this configuration to rigorously evaluate the computational advantages of our method. Furthermore, we conduct a comparative analysis between our proposed method with partial healing and the complete model healing approach. As demonstrated in section 1.14, our methodology requires only the healing of the LT component while maintaining competitive performance relative to the full model healing. For the UDL baseline, we adhere to the original implementation of the offers, which employs low RA-based healing exclusively on NMLP layers, as demonstrated in Fig. Duration, emissions, energy, performance metric 100 million 100 1102 relative performance log scale 1.0 times 1.0 times 1.0 times 6.6 times 3.5 times 3.5 times 107.7 times 77.5 times 77.5 times 170.1 times 107.2 times 107.1 times normalized performance comparison relative to best in each category. Methods: ReplaceMe ALS, ReplaceMe cosine, ReplaceMe with healing only LT, UDL with healing. Figure 4, comparison between ReplaceMe and UDL in terms of computation and environmental impact. 4, a comparative analysis of our two proposed methodologies is presented. The ALS approach offers significant advantages in terms of cost efficiency, speed, and the reduced demand for computational resources and memory. However, this method incurs a slight decline in performance metrics. Thus, the choice between these methods should be informed by the specific requirements and available hardware resources of the user. Adopt 9 mergeable LTVS. LT is an independent block. LT objective AVD accuracy complexity RP fusible into MLP cosine 0.634 15.875 0.905 separate LP block cosine 0.640 13.481 0.913. Table 10. Compressing Llama 3 AP by 25% using a cosine distance objective without applying healing. This involves applying LT on the MLP output or on the full output activation of the transformer block. 18. In our work, we propose integrating the linear transformation LT matrix so that it can be merged with the dump projection component of the NLP layer, preserving architectural compatibility with standard LLM designs. However, this approach raises a critical question regarding the comparative efficacy of injecting the LT as a mergeable layer versus incorporating it as an independent, non-mergeable block within the transformer architecture. In Table 10, we present the outcomes of integrating the linear transform LT directly into the multi-layer perceptrons MLP dump projection through matrix fusion. This approach ensures parameter efficiency in contrast to employing a standalone LT block, where the LT functions as an independent layer between transformer blocks, thereby introducing additional computational overhead. The results demonstrate a marginal improvement. However, the extent of this improvement is contingent upon user-specific requirements. Adopt 10 block selection analysis. In this section, we conduct a systematic ablation study to investigate the relationship between interlayer activation distance metrics and model performance under sequential layer removal. We employ a sliding window approach, iteratively pruning contiguous blocks at 8 layers starting from the initial layer index and incrementally shifting the window by a single layer position. For each configuration, we quantify activation dissimilarity using both cosine distance and L2 norm, computed between intermediate activations of the original and pruned models. Subsequently, for our method, we estimate the linear transformation LT and evaluate the pruned architectures on a standardized subset of benchmark tests. As demonstrated in Fig. 5, we observe a straw inverse 0.3, 0.5, 0.4, 0.45, 0.5, 0.55, 0.6, accuracy 0.25, 0.3, 0.35, 0.4, 0.45 cosine distance accuracy in this distance 0.2, 0.4, 0.6, 0.8, 1. L2 distance cosine dist atom, cosine dist LS, cosine dist UDL, trendline atom cosine, trendline LS cosine, trendline UDL cosine, L2 dist atom, L2 dist LS, L2 dist UDL, trendline atom L2, trendline LS L2, trendline UDL L2. Figure 5, comparative analysis of distance metrics and predictive accuracy across layer pruning configurations. Trendlines illustrate the inverse correlation between cosine distance and accuracy, contrasted with positive correlation between L2 and accuracy degradation. Results are shown for ReplaceMe with LT estimation by cosine/LS metrics and UDL baselines. Correlation between cosine distance reduction and accuracy improvement across all methodologies. Specifically, ReplaceMe with cosine-based LT estimation achieves peak performance at the lowest cosine distance values. Conversely, configurations exhibiting lower L2 correspond to significant accuracy degradation, suggesting that L2 lacks power for optimal layer selection. In Fig. 6, we present the detailed results of sequential layer removal and compare the cosine distance with other similarity measures, CKA 20 and CCA 32. We observe that the highest accuracy corresponds to the lowest cosine distance, which confirms the validity of using cosine distance as a block selection criterion. 19. It is also important to note that the optimal pruning range depends on both the architecture and the number of layers removed. Previous works have also observed that layers form natural groups. 49. We conducted a similar experiment and plotted the cosine distance across all layers in Fig. 7, 1 to 92 to 503 to 514 to 525 to 536 to 547 to 558 to 569 to 1910 to 1811 to 1912 to 2013 to 2114 to 2215 to 2360 to 2417 to 2518 to 2619 to 2720 to 2821 to 2982 to 2023 to 2524 to 32. Pruned layers 0.1, 0.2, 0.3, 0.4, 0.5, 0.6 metric value. AVD at cosine dist 1 CCA, 1 CKA. Figure 6, comparison of cosine distance CCA and CKA across all 8 layer pruning configurations in Llama 3 AP. Adopt 1 cosine distance approximation. In this section, we discuss further our proposed approximation of the loss, where we subtract the attention output from the activation after the cut. When using the cosine distance, first we revisit the original at 14 T asterisk equals argmin T cos MIT plus Y I plus N 14, where we observe that in order to estimate T numerically, we need to store 3 activations, I Li plus N for each token. This is not effective and requires considerable memory and time to compute. To overcome this issue, we apply the cosine distance after subtracting the attention output from a full activation at the end block of the cut is formulated in at 15 T asterisk equals argmin T cos MIT IT li plus n minus yi. 15. As evidenced by the experimental results presented in Table 11, the approximated cosine formulation, model method, Pruning layers, calibration, data training, state, perplexity, AVDA. Llama 3 AP instruct approx loss 8 slim, orca no training 15.880.634. Llama 3 AP instruct org loss 8 slim, orca no training 16.630.630. Q1 2.57b instruct approx loss 7 slim, orca no training 7.920.591. Q1 2.57b instruct org loss 7 slim, orca no training 10.600.580. Llama 3 AP instruct multi approx loss 8 slim, orca no training 13.950.628. Llama 3 AP instruct multi org loss 8 slim, orca no training 13.120.630. Table 11. Comparison between the original loss and the approximated version. The approximated version makes use of the cosine distance between the transformed NLP output and the residual of the activation of I plus NTH block and the attention of the TH block achieves comparable performance to the exact loss computation with marginal improvements. Observe, this approximation yields memory efficiency gains, requiring only 2 stored activations per token li plus n minus yi, thereby reducing memory usage by approximately 66% relative to the original implementation. 20. 024681012141618202224262830. Sample index 02468161241 sample index cosine distance infusion matrix 0.1 0.2 0.3 0.4. Figure 7. Average cosine distance between hidden states of layers for Llama 3 AP. Each cell ij shows the mean cosine distance between the output vectors of layer E and layer j computed across 256 samples of slim orca. But F12 data ablation 0.1 0.4 0.8 1.2 1.6 10400.2 0.4 0.6 0.81. Calibration samples average accuracy v test. Calibration samples ls cosine Llama 3 AP baseline 0.1 0.4 0.8 1.2 1.6 1,041,020. Calibration samples perplexity vs. Calibration samples figure 8. Pruning Llama 3 AP by 25% using different number of samples to estimate the linear transform. Impact of calibration dataset size. Figure 8 illustrates how the size of the calibration dataset affects the linear transform estimation for both the L2 and the cosine distance objectives. Although increasing the number of calibration samples does not significantly improve benchmark accuracy, it does substantially reduce perplexity, especially when the cosine distance objective is considered. The linear transformation matrix has shape d times d, requiring approximately n equals d2 tokens for reliable estimation. With a per sample sequence length of s, this translates to at least d2/s samples. For example, in Llama 3 AP, where d equals 4096 and s equals 1024, about 16,000 samples are theoretically 21. Needed. However, as seen in Fig 8, accuracy remains stable even with as few as 1,000 samples, suggesting robustness to sample size. That said, perplexity continues to improve with more data, indicating better model confidence and predictive quality. Impact of masking for data augmentation. We have also investigated random token masking as a lightweight data augmentation technique for scenarios with limited calibration data, e.g., 1,000 samples. As shown in Table 12, masking improves the stability of the numerical optimization and leads to better convergence when estimating the linear transformation. This masking strategy proves especially beneficial in low data regimes where it reduces overfitting and enhances generalization. However, when more data are available, the impact of masking becomes negligible. In summary, a calibration dataset with approximately d2 tokens ensures stable and accurate estimation. When working with fewer tokens, random masking can mitigate overfitting and improve estimation quality. For instruction-tuned models, instruction-style calibration data consistently leads to better pruning outcomes, while self-generated data can reduce perplexity. It may degrade benchmark accuracy, highlighting a trade-off between confidence and task-specific performance. Model masking calibration data AVD compare perplexity down percent up. Llama 3 AP 0.6973.1 100.2. ReplaceMe 1K 0.632 24.96 90.62. ReplaceMe 1K 0.6342 1.08 90.91. ReplaceMe 8K 0.633 15.88 90.76. ReplaceMe 8K 0.632 15.69 90.73. Table 12. Random token masking during the estimation of the linear transformation contributes to a more stable solution, particularly when working with small datasets. Adopt 1 3 extra model evaluation. To further validate the efficacy of our pruned models, we conducted an additional evaluation on a new subset of benchmarks derived from the Huddy Face Leaderboard 10, utilizing a modified version of Harness 12. This benchmark set encompasses Big Bench Hard BB8 comprising 23 complex and diverse tests 50, high school level mathematical competition problems 17, PhD level domain expertise assessments across disciplines 39, algorithmically generated intricate problem sets 44, a refined version of MMLU benchmark 54, as shown in Fig 9. The normalized results demonstrate that the Llama 2 model preserves performance across nearly all benchmarks post-suppression. Notably, Llama 3 variant has a marginal performance degradation on the mathematical benchmark potentially attributable to task-specific sensitivity to parameter reduction. Depending on the user's specific needs, an additional healing process can be considered to overcome this issue. Adopt 1 4 healing experiments. Here, we present a comparative evaluation of our method in 3 experimental configurations. 1. The baseline implementation without any healing mechanism. 2. Partial healing of only the learned linear transformation LT layer. And 3. Complete model fine-tuning using a subset of the C4 dataset. Method training terms race winner and QA bool Q open book QA sci Q perplexity AVD at Llama 2 7B num 0.3952 0.7427 0.7900 0.7783 0.44 0.9050 3.3973 0.6752. Replace me num 0.3656 0.6977 0.7051 0.7263 0.3460 0.8370 22.3586 0.61295. Replace me only LT 0.3799 0.7182 0.7350 0.7728 0.3760 0.8840 5.3965 0.64432. Replace me full model 0.3847 0.7056 0.7416 0.7835 0.3920 0.872 4.9138 0.64657. Table 13. Performance comparison of ReplaceMe with without healing and with different trainable parameters. As demonstrated in Table 13, the model variants which involve healing yield performance improvements. Notably, the LT-only healing approach achieves comparable accuracy to the full model. 22. BMath GPQA, Musser, NMLU Pro 0.2, 0.4, 0.6, 0.8, 1.0, 1.2. Llama 2 models normalized to baseline. BMath GPQA, Musser, NMLU Pro 0.2, 0.4, 0.6, 0.8, 1.0, 1.2. Llama 3 models normalized to baseline. Baseline UDL LS cosine figure man. Comparison between our proposed methods and UDL on a different set of benchmarks. Results are normalized relative to the baseline model performance. Fine-tuning while offering substantially reduced computational costs. This selective healing strategy demonstrates superior efficiency compared to alternative healing approaches documented in prior work. Adopt 1.5 computation environment. All experiments were conducted using an NVIDIA A100XM4-40 GB GPU with an AMD EPYC 7742 64 core processor running Ubuntu 22.04 and Python 3.10. The software environment environment was based on the official NVIDIA PyTorch containing for .io/NVIDIA/PyTorch 23.10 For additional testing and validation, models were also tested on a P100 GPU using the Kettle environment, which imposes stricter compute and memory constraints. The computational setup and training configurations are summarized in two tables. Table 14 details the hyperparameters for ReplaceMe cosine, and Table 15 compares the two healing experiments. Training only LT versus full model fine-tuning. Parameter value, optimizer atom, learning rate, data point, PA1, batch size 1024, epoch 10, loss function, cosine distance loss, weight initialization identity matrix, bias false. Table 14, hyperparameters and configuration for ReplaceMe cosine-based train. .16 multilinear transformations. To isolate the impact of number of LTs, we fix the total pruned layers at 8 and vary how many of those are implemented as LT 1, 2, 4, or 8. Then benchmark both Llama 3-8B instruct and Mistral 7B instruct D0.3 on the same benchmarks. We approximate using ReplaceMe LS method. Table 16 summarizes the results. 23. Parameter only LT training full model training. Optimizer atom context length 2048 learning rate 3E41E5 number of GPUs 14 batch size per device 11 max steps 80,000 20,000 gradient accumulation steps 11 gradient checkletting true unfrozen weights LT only full model trainable parameters 16.8 and 6.3b. Table 15 hyperparameters for healing experiments full transforms full model method number of LTS race winner and pi QA bool Q open book QA IQ perplexity AVD Llama 3-8B instruct ReplaceMe 10.3694 0.7167 0.6844 0.80 610.33 0.84 21.2 610.6244 ReplaceMe 2 0.3885 0.7261 0.6872 0.7798 0.3380 0.858 18.9853 0.6296 ReplaceMe 4 0.3751 0.7277 0.6953 0.7661 0.3240 0.8590 6.0669 0.6245 ReplaceMe 8 0.3876 0.7017 0.6834 0.7165 0.3360 0.830 37.976 0.6092 Mistral 7B instruct E0.3 ReplaceMe 1 0.4105 0.753 0.6893 0.856 0.340 0.878 0.859 0.6545 ReplaceMe 2 0.4134 0.6156 0.7486 0.6985 0.3580 0.902 7.1119 0.6227 ReplaceMe 4 0.4182 0.7119 0.7040 0.8287 0.3640 0.9140 5.913 0.6568 ReplaceMe 8 0.4077 0.6551 0.7318 0.8174 0.382 0.912 5.9897 0.6510 Table 16 performance comparison of ReplaceMe LS with a different number of LTs. We fixate total of 8 pruned layers and vary how many LTs we insert. Reported our test addresses on the same set of benchmarks for both Llama 3-8B instruct and Mistral 7B instruct V0.3 for both models. Using 2 or 4 LT modules tends to offer the best trade-off between task performance and language modeling quality. However, the differences across configurations are relatively small and results are largely comparable. Fewer LT modules may under-depth the prune model, while more modules can introduce unnecessary complexity. The adaptation method appears robust to moderate variation in the number of LT modules. At 17 task-specific LT, we ran an additional experiment to see how the choice of calibration data affects results. In this test, we used the training card of the Sci2 dataset as a calibration data and then measured performance on its test set. For comparison, we also applied our method using card of the general Slim Orca dataset, but still evaluated it on Sci2. Using the Llama 3-8B model, we found that calibration data from the same test leads to much better accuracy than calibration with general purpose data. This shows that tailoring calibration data to the target task can significantly improve compressed model performance. See the results in Table 17. Model calibration data compression SIG accuracy. Llama 3-8B instruct 0.93. UIDL SIG task specific 25% 0.687. Or LSDSU SIG task specific 25% 0.89. Or LSDSU Orca general 25% 0.858. Table 17. Performance comparison of Llama 3-8B models calibrated with task specific Sci2 train. Split versus diverse open source Orca subset datasets on a Sci2 test split 24.